Hey everyone, my name is Santosh Gupta, and I'm presenting a Claude Fable generated prediction on what it thinks Part 2 would look like in the 3Blue1Brown series on entropy and compression. So at the time of this video, Part 1 came out about a month ago. Part 2 has yet to be released. And I took the transcript from part one and gave it to Claude Fable and asked it to generate what it thinks part two would look like. So it generated these animations and slides. It also generated a script, but I found it hard to follow. So I'm just going to ad lib through the presentation. So it starts out with an equation for the cross entropy, and it says it's the cost of the mismatch between the actual probabilities and the model predicted probabilities. It also has this tagline, reality writes the checks, your model sets the prices. Um, I'm not sure what that means. If you have an idea, please leave a comment. But for now, I'm just going to ignore that. This next slide is a recap slide from part one in the series. So in part one, we learned that the less likely an event is, the more surprising it is. And so the more information it carries. On this graph, we have probability on the x-axis, information on the y-axis, information given in bits, and the equation for the information is negative log 2 of the probability of the event. So an event that has a 1 in 2 chance of occurring, that carries 1 bit of information. An event that carries a 1 in 8th chance of occurring, that carries 3 bits of information. And the slide also recaps the robot example from part one, where the robot moves up half the time, down quarter of the time, left an eighth of the time, right an eighth of the time. And the clever student, they came up with a solution to use 1 bit to encode the up instruction, 2 bits to encode the down instructions, 3 bits to encode the left, 3 bits to encode the right. And that follows the probability information curves exactly. Um, so since the clever student solution, it follows the distribution exactly, the average number of bits per encoding, that's also the entropy. So backing up a bit, so we can calculate the average number of bits per encoding by multiplying um, the probability of the event by the number of bits used to encode the event and multiplying all of those up. So 1/2 times 1 bit is 1/2. 1/4 times 2 bit is 0.5. 1/8 times 3 is 0.75 for each the left and the right. And if we add all these numbers up, we get 1.75 bits per encoding per movement. Um, and so since this follows um, the true distribution exactly, it follows this probability information curve. Like here we have an event that has a half, like 50% chance of occurring, and this carries 1 bit information. So since this follows the true distribution exactly, um, this total area or average bits per instruction. This is also the entropy, which is defined as the theoretical minimum average bit cost determined by the true distribution. Um, so yeah, this is a recap slide from part one. For this next slide, um, it seems like a recap slide to me, but I don't think Claude Fable intended this to be a recap slide just from looking at the script and reading the text in the slides themselves. But it goes over the naive student solution and the clever student solution. The naive student used 2 bits per movement. The clever student used 1 for up, 2 for down, 3 for left and right. And it's saying that each of the solutions, they have an implied belief about the probabilities of the movement. So the naive student gave a 1 in 4th chance of each of the movements occurring, whereas the clever student, they encoded to the actual probability distribution of the robot. And Claude Fable is saying the naive student was never sloppy. They were just optimal for a different universe. So maybe it's like defending the first student. Maybe it's saying the first student had different assumptions about the uh, probability distribution. Um, but I thought, yeah, maybe this was already pretty covered in part one, even though it seems Fable's trying to make a new point. For this next slide, um, I don't think Claude Fable intended this to be a recap slide. I think it thinks it's showing something new. Uh, but I think part one kind of did this exact same thing. Like they had the exact same visual, uh, with the length of the 1 bits covering 50%, 2 bits covering 25%, and so on. Um, but yeah, to give Claude Fable credit, it didn't actually watch the video, it only looked at the transcript. So can't fault it too much. Faded regions sit above the chosen word, prohibited by the prefix-free rule. Yeah, I think uh, part one like went over this pretty well, like way better than this slide. Um, again, uh, can't really fault uh, Claude Fable here. This next slide, it gives a visual of the cross entropy uh, for a wrongly assumed probability distribution and how that compares to the correct probability distribution. So on the left, it uses a coding schema that assumes a like a totally wrong probability distribution. So it thinks up is happening 1/8 of the time instead of 1/2 the time. It thinks down is happening 1/8 of the time, left 1/4, right 1/2. And so on the left side, it uses 3 bits of information to encode up, since it thinks up is only going to occur 1/8 of the time, and the other directions have corresponding bits to encode its what it assumes to be its uh, probability of happening. Um, and so we can calculate the cross entropy by multiplying taking the sum of the products of the assumed information times its true probability. So 3 bits times the true distribution of true probability of 1/2 is 1.5, and so on for the other three directions. And so if we add them all up, we get 2.625 average bits per movement. Compare that to an encoding that assumes the true probability distribution. Um, that gives 1.75 bits per movement, and since the true distribution matches the actual, since the assumed distribution matches the true distribution, this term just turns into the entropy again, which is the lowest possible average bits per event. And on the bottom, we have um, the equation for the cross entropy. It's the sum of the true probability of event times log 2 of 1 over the assumed probability. And if you remember from a few slides back, this term right here, log 2 of the 1 over of the assumed probability, that's the information uh, for that assumed probability. The assumed carried information. So for the up instruction, which has an assumed probability of 1/8, if you take log 2 of 1 over 1/8, uh, that gives you 3. Uh, if you take log 2 of 1 over 1/4, that gives you 2. So so this is like another way of saying the sum of the true probability of the event times um, the assumed carried information of that event. This next animation, I'm not really sure how, like, what the point is. It's just making the left side look exactly the same as the right side. Um, but we already have the right side, so I'm not really sure what the point of that was. But this next one is more interesting. It shows a visualization of the cross entropy when the encoding assumes equal probabilities of each of the events. And then it goes back to the original, totally wrong uh, probability distribution assumption. So this slide, it shows how our three probability distribution coding schemas, like 3 different assumed probability distributions and their corresponding coding schemas, how they encode the same 16 sampled directions. Um, so the first one that assumes the true probability distribution of these directions. Uh, so as you can see, it uses 1 bit per up, 2 for down, uh, 3 for left, 3 for right. So to encode these 16 movements, it takes 28 bits. For a coding schema that believes in a uniform distribution, it takes 32 bits, so more than the first one, since the sampled 16 movements, they don't follow a uniform distribution, they follow the distribution uh, for that's assumed in the first encoding schema. And then for the totally wrong coding schema, like the coding schema that assumes a totally wrong probability distribution of the movements, that takes the most 42 bits. So this slide brings up the concept of the KL divergence. So here we have a visual of the cross entropy for each of the coding schemas. For the top one, since the assumed probability distributions are the true probability distributions, the cross entropy is just the entropy, which is the lowest possible average bits per event. But the other two, it can be thought of as the entropy plus some other term. For the middle one, that's 0.25. For the last one, the totally backwards assumption that it's 0.875. And that term is the KL divergence. Sorry, KL divergence. And the properties of the KL divergence is that it can only be greater than or equal to zero, and it's only equal to zero when the assumed probability distribution is the true probability distribution. So the purpose of this slide was to show that the KL divergence can never be negative. Um, there were some animations, but I decided to skip over them. I didn't think they were that interesting, and I think most of the visual is at this part of the slide. So the KL divergence, it's the sum of this term for each of the events. On the left side, you have instances where an event was um, underestimated, and on the right side, you have events that were overestimated. And as you can see, the terms on the left side are greater than the ones on the right side. And at the bottom, you have uh, each of these terms being summed up. And at the end, you have a positive number. Um, so this is just giving a visual of Gibbs inequality that says that the KL divergence can never be negative. This slide transitions to language modeling, specifically the bits per character for various language models. The most elementary being a language model that gives equal probability of all 27 characters. That gives an average bits per characters of 4.76. If you take a corpus and just count the frequency of each letter and assign a probability based off of that, you lower the bits per character to 4.1. If you take the frequencies of two letters appearing together, you can decrease down to 3.3. If you do word frequencies, it decreases to 2.6. And this one, 1.3, this is from part one of the series where Claude Shannon did an experiment with his wife where he would read through a book and have his wife guess the next character. And so from that experiment, Claude calculated a bits per character of 1.3. And maybe language models have a bits per character of zero point 0.7, maybe Claude Fable isn't sure. And then the entropy of English is somewhere below all of this. Uh, can't be measured directly, but it's definitely somewhere below um, the best language model. This slide covers cross entropy loss in language modeling. So here we have an example of an LLM trying to predict the next word in the sentence, the cat set on the blank. And currently it thinks Matt has a 0.35 chance of being correct. And then say that that's what actually came next in this training example. So we assign a true probability of 1 for Matt and 0 for everything else. Um, the cross-entry loss is the probability of that event times log 2 of the predicted probability, or in other words, the true probability times the carried information from the predicted probability. And since p of x is 0 for everything except for mat, this term reduces down to negative log 2 of q of mat, and q of mat is 0.35, so that is 1.51 bits. And so at this point, I have to refer back to the original script given by Claude Fable because I didn't quite get the point of this slide. So in the script, it says the model gave Matt a probability of 0.35. So this training steps loss is negative loss log base 2 of 0.35, about 1.51 bits. And that number is a code length. A compressor built on this model would spend exactly 1.51 bits encoding Matt here. So yeah, I think I get that. So if he had a compressor and encoded um, each of these words using a certain number of bits, maybe Matt would get 1.51, sorry, 1.51 bits in situations where uh, the cat set where we're trying to predict the next word in the cat set on the blank. Um, and then in the next part of the script, it says the LLM isn't literally writing codes like in our robot directions example, but its probabilities imply code length. High probability means fewer bits, low probability means more bits. So what Fable is saying, the training loss is the average number of bits those implied codes would spend on the real next tokens. Um, I quite don't get that. Uh, hopefully the next 3Blue1Brown video would illuminate me. If there is a actual point to be made on the slide. But I'm stuck here, so I am just gonna move on. This slide was really just interesting. It reframes the pre-training of a language model as a compression task. Um, so on the x-axis, we have the training tokens, y-axis, we have the cross-entropy loss, aka the bits per token. Um, so at initialization, um, each of the tokens is equally feasible, or the language model assumes that each of the tokens is equally feasible, and so it gives an average of uh, 15.6 bits per token. So that's negative log 2 of 1 over 50,257. If you're wondering where this number came from, I think that's the um, number of tokens in the original GPT-2 tokenizer. And so the animation shows that at the start, each of the tokens is equally probable according to the language model. Uh, Here we have, I believe 7.4 is the KL divergence, and H is the entropy of language, or the theoretical entropy of language. And as training continues, the KL divergence shrinks, but the entropy stays constant. This slide covers perplexity. Perplexity is 2 to the cross entropy. So Basically the same model is confused as if they're n-sided dice. So for if the loss is 1 bit to the 1 equals 2 different possibilities. If the loss is 2.585 bits, 6 possibilities, and so on. So Claude Shannon's experiment, it had an average of 1.3 bits per character. Um, and so it's rounded off to 1 in the sentence, so that gives a perplexity of 2. So it's saying reading on average is 1 good yes, no question per letter. And that's a pretty interesting way of thinking about it. I'm going to skip the slide. It's on distillation, uh, but it didn't seem too related to any of the the more groundbreaking stuff covered in these slides so far. It just seems uh, like if you study distillation, I don't think it's anything new, and I don't think it's related to like the main the main thesis of uh, these slides. I'll post the original script in case I'm missing anything, but um, yeah, this seems more like a detour, so I'm going to skip it. So I think this slide is a recap of everything so far, or maybe like a summary. Um, Prediction is the same thing as compression. It was like the point it was making this whole time. Um, and then it does a transition into the very last topic. Um, gzip, it's like a compressor that was covered at the end of the original series. This next slide covers the gzip algorithm or compressor. Might seem like a detour, but it's actually pretty useful for this next part that kind of ties everything together. So say that we have two sentences that come right after another. The cat sat on the mat, new line. The cat slept on the mat. So two pretty similar sentences. And you might be thinking there might be a way to uh, compress the second one since it's so similar to the first one. So what gzip does, it takes these segments that have appeared before in the text and replaces them with a reference. So in this example, it replaces the cat with the numbers 24, 8. And so what these two numbers represent, so 24 is the number of characters we go back to find the original reference to the cat. So say we go, so starting from here, we go back a new line, that's one character, and then if you go character by character, if you go back 24 characters, we go to the beginning of the sentence. So that's going back 24 characters. And then the length of the segment, including the spaces, that's 8 characters. So that's what this represents. And then it's similar for this one. If you go back 26 characters, we go to the beginning of this segment, and then this segment is 12 characters long. So that's how the gzip algorithm works. So yeah, it says copy 8 characters from 24 characters back, and the second segment is copy 12 characters from 26 characters back. So that's how the uh, gzip compression algorithm works. So for this part, Claude Fable actually ran experiments on this computer for this part. So it took a passage that was translated into Spanish and Portuguese and compressed them individually, and that came out to 246 bytes total, and then it concatenated the passages and compressed them, and then it came down to 195 bytes. So there were 51 bytes of shared structure between the two translation. And then it did the same thing for Spanish and Polish. Uh, Separately, 250 bytes, concatenated 217 bytes. So there were 33 bytes of shared structure. Another thing, it used zlib instead of gzip. Maybe gzip wasn't available on my computer. But I think this was pretty interesting. So using compression as a measure, Spanish and Portuguese is more similar than Spanish and Polish. The difference is 51 bytes to 33 bytes. And then it covers this formula. It's called the normalized compression distance. It's a better way of measuring the distance. It's distances of to text using compression, using these terms. I'm not going to go over it, but if you want to look it up, it's called the normalized compression distance. So here again, Claude Fable ran this experiment on my computer, which is pretty cool. But using the NCD distance of different combinations of languages and clustering, uh, it found the most um, similar languages to each other. So Spanish and Portuguese were similar, Dutch and German, Czech and Polish, and then it did a clustering of the next languages, so French, Italian, that were all clustered together, and these make up the Romance languages. Um, Czech and Polish, they're the Slavic languages. They went together. Dutch and German are Germanic. Um, and then even though English is a Germanic language, it was more similar to the Romance languages than uh, Dutch and German. Maybe that's because English has a lot of French words to it, French words in it. So maybe that's why I got paired more with the Romance languages. But I think we saw a preview of this in the end of part one. It'll be interesting to see if 3Blue1Brown did the same thing and if uh, these results will be similar to what he got. So this is the last slide in the presentation. It's a preview of part three in the series, which was also given in part one of the original series. I'm not sure what's going on. I think it's maybe the probabilities of the of an entire sentence, or like the information of an entire sentence. I wasn't quite sure even after looking at the script. I'll post the script, and if anyone has an idea what was in it, then please leave a comment. But for anyone who stuck around uh, this long, thank you so much. It was deeply appreciated.